I'm getting better at this, guys. I remember that I have to record. Very good. Okay, so let's just quickly go over what we did last time around. And so we started off by looking at, these conformal transformations once more, and we discovered that when if we look at the two-dimensional version of our earlier equations, 2.4 and 2.5, then we end up with the Cauchy-Riemann conditions. These are our Cauchy-Riemann conditions. As you would know, a complex function whose real and imaginary parts satisfy this equation, this will be a holomorphic function in some open set. Okay. So now what we do is we take so we take, epsilon to be epsilon naught plus I epsilon 1. So, and epsilon bar to be epsilon naught minus I epsilon 1. So since epsilon z is holomorphic, then if you have some function f of z, which is z plus epsilon z, this is also going to be a holomorphic function. This is going to give rise to an infinitesimal to the conformal transformation of z going to f of z. Okay. Now we wanted to look at what the generators of this particular transformation are. For that, what we did is we required this epsilon of z to be actually in general meromorphic with on the plane. So that is, it has isolated singularities outside this particular open set. And what we are going to do is we're going to perform a LoRa expansion of this epsilon z around for, say, z equal to 0. Okay. So now if we do that, so what we end up with is this infinitesimal transformation z prime, which is z plus epsilon z. This epsilon z can now be expanded in terms of this LoRa series, and that's given by these infinitesimal parameters epsilon n, which are constant, and these zns. Okay, very good. Now, so it's very straightforward to see that if you have something which is z to the n, this is going to be generated by these small ln's, which are z to the n plus 1 del z. I think there are a few more people waiting. Let me just admit them. Okay. Yes.
Sir, can you, actually my internet connection is quite not good. So
okay.
Can you please turn off the waiting room so that if I get disconnected, I can get connected automatically?
Yeah, that's a very good point. Thank you for bringing this up. Let me try and see if I can actually do this right away. Just give me a second, guys. Let me try and see if there is enable waiting room. So I've disabled it. So anybody with this can just get in. Thanks for just saying this out loud, because this, I think, happened to you once in the last lecture or something like that, Shivam, right?
Yeah.
Yeah, sorry about that. And it's a little hard for me to keep track of who's going and who's coming out. So apologies for that. But hopefully this waiting room nonsense that we had is not there anymore. And unfortunately, what is also not there anymore is this link up with my iPad, which is really getting on my nerves now. Just let's see if I can actually make this situation a little better. Give me a second, guys. Let me see if I can simplify my life a little bit more. Yeah. Okay. I will stop sharing. Just give me a second. I'll try and see if I can. Okay. Let's see. This is not helping me, unfortunately. Okay, I was not able to simplify my life, then I have to again go back to doing the same thing again. Okay, apologies for the delay. I'm just trying to figure out some software issues which I've not been able to figure out at the moment in real time, but hopefully next time around I'll try and fix this notoriously problematic thing keeps appearing again. Okay, so we are saying that we're looking at these infinitesimal transformations, and so if we expand this in LoRa series around z equal to 0, these are the coefficients that so these epsilon n's are infinitesimal parameters that are constants. And it's very straightforward to see that something like this is generated by ln as z to the n plus 1 times z. So the point essentially is that just look at e to the ln into on z, and then you'll see that this is so e to the ln some. If you just act it on z, this is just e to the minus z and plus 1 del z acting on z. So this just gives you, at the end of the day, if you expand it out, so you'll need to have some small parameter epsilon, say alpha here, and this just gives you some alpha into z to the n plus 1. Okay, so that's what you will get. And so that essentially means that so these guys, these lns are the ones that generate for you these infinitesimal transformations. So what we did next is we calculated the brackets of Lm with Ln, and that turned out to be n minus nl plus m. And we saw that there were two copies of this. This is what was called the Witt algebra. So this is what is the Witt algebra. And then we saw that there was another copy with the L bars, and L with L bars give you 0. Okay, so this was two copies of the Witt algebra. And this is the infinitesimal. So this essentially shows that the algebra of infinitesimal conformal transformations in d equal to 2 is actually infinite dimensional, because these are labeled. So this labels n runs over all z. Okay, so this goes all the way to minus infinity to plus infinity for all integers. So you have an infinite dimensional set. Now what we did is so that was ln. So these were defined for all n and m for all integers. Now what we did is we wanted to ask the question of which ones of this were defined properly defined everywhere. And there we saw that for one you could you could see that if you have this expression, and this is only going to be non-singular at z equal to 0 if n is greater than equal to greater than equal to -1. When you want to go to infinity, this happens when n is less than equal to +1. So the globally defined conformal transformations on this Riemann sphere are going to be generated by L -1, L0, and L +1. So this is what generates the conformal group. So L -1 gives you translations. L0 gives you when you write Z as R e to the I phi. So this gives you that L0 plus L0 bar are your dilatations, and L0 minus L0 bar are your rotations. And you will also find that L +1 actually corresponds to special conformal transformations. So all of these taken together, I mean, form this particular general transformation of Z goes to AZ plus B by CZ plus D, where A, B, C, D are given are valued in C. Okay. For these to be invertible, AD minus BC has to be has to be not equal to 0, and we can scale these ABCDs such that we can make AD minus BC equal to 1. Okay, and we also note that if we look at this particular transformation and we do a change, take A to minus A, B to minus B, C to minus C, and D to minus D, this particular transformation stays the same. So there is a Z2 factor here. So what is going to happen? So the upshot of this whole business is that the conformal group on the Riemann sphere is this group SL2C modded out by Z2. Okay. So these are, so ABCDs are essentially, so SL2C, as you can understand, give you the group of matrices with complex entries ABCD such that the determinant is equal to 1, and we have modded out by Z2 because we also pointed out that all of these guys going to minus themselves keep this transformation unchanged. Okay, so this is what is also called the Mobius group, and this is going to be the conformal group in D equal to 2. Now we said something interesting, and this is something that we didn't really. So I said that the Witt algebra admits something called a central extension, and the central extension of a Lie algebra is so it is going to be, it's if you have a Lie algebra G and you want to extend it by C. So this is going to be, so the brackets will take a changed form like this, where if your x tilde, y tilde are in G tilde, these will turn out to be x, y, and G, plus some C, some number times some particular function of x and y. We call this P. And it's this particular C is called a central extension. This is going to, so if you take this and commute with any other generators of G tilde, this is going to give you a 0. Okay, so that is a formal definition of what a central extension is. Now I said that when you are looking at the Witt algebra, the Witt algebra actually admits some sort of central extension like this. And what you find is, so this part is the Witt algebra, and you have something else like this. Okay, so some other piece that looks, when you do the math, you'll see that the extra piece looks like this thing where C is a number, and the function of PMN takes the form of n cube minus n delta n plus m0. So the point here is that what do you do? I mean, what is sort of what sort of points out that a particular algebra, you can write down whatever algebra you want to write down, but you can write down some sort of bracket. But how do you know that this is going to form a well defined algebra at the end of the day? For that, you guys notice that there is something called the Jacobi identity. So let me just put a page in. So if you have elements A, B, C there, then you know that A comma BC plus C comma AB plus BCA, this has to be equal to 0. So this is what is called the Jacobi identity. And for any sort of algebra, if you want to define some particular algebra with generators A, B, and C, then this is something you can write down something like A, B is something F into C, and the rest rest of the things in some way. So if you write down something of a form like this, and BC is something else, and CA is something else, so you have to make sure that all of these guys actually give you at the end of the day something that satisfies this particular Jacobi identity. So what you can do is you can check that 3.11, for example, is something that satisfies the Jacobi identity. Actually, we arrived at this expression of PMN by employing the fact that it's going to close under Jacobi identities. The trivial thing, of course, is that if you can't find something like this, there is no central extension if you wish. But there's a clearer way of trying to understand. This more mathematical way of trying to understand this as well. And this is something that we will not go into in the course, but for those of you who are mathematically inclined, the central extension is also related to something called a second chromological group. So this, classifies all central extensions of the algebra G. So if this is equal to 0, yeah, in that case, that particular algebra will not have any central extension. For example, if you have a finite dimensional semi-simple Lie algebra, then for them this H2 is equal to 0, and that means that there cannot be any central extensions to that algebra. Okay. So we will actually, I'll try and give you homework in these next few days, where you would be able to see that there are central extensions to finite dimensional algebras as well, and it occurs closer to home than you might think. Okay, so you'll see this in the next assignment that you guys will have to work out. So another thing that I try to point out is when you're looking at this and you're looking at the structure of PMN, you see that PMN is equal to 0 for n is equal to 0 plus minus 1. So for the global subalgebra, there are no central extensions. You already know that this is going to be the SL2C mod Z2. So this was going to be this is sort of a reflection of the fact that this is a semi-simple finite dimensional Lie algebra, and hence this does not have any. I mean, this will not have any central extensions. So that was that. That was a reminder of what the Witt algebra was and what the Virasoro algebra was. So just remember that the Virasoro algebra, if you wish, is a quantum mechanical extension of the Witt algebra. Just the extra thing that you have to add here is something which has a central charge. So this C is going to be called a central charge. We will see. We will see. We will see that C has a lot of there is a lot of physics in this number C. We will get to this again and again as we go ahead in the next few lectures. Okay. Does that answer the question that you guys had about the distinction between the Witt algebra and what the Virasoro algebra is?
Yes, sir. So just one.
Please.
Just one thing. When you were writing the direct sum, that was direct sum of vector spaces, right?
Direct
Between
sum
Witt and
of direct sum where? I was writing down a direct sum here.
Virasoro algebra definition.
So here I'm looking at the, so this is a Lie algebra G tilde. This is another Lie algebra G. Okay, so that's what we had, and we had briefly in the last class. So let me actually get rid of this page. Just give me a sec. Okay, where were we? Yeah. Okay, so today we want to go on to try to understand our other things that so we tried to define what a primary field, etc., was last time around as well. So we defined, so we said that we are going to be looking at fields which are dependent on Z. So these are going to be called chiral fields or holomorphic fields. And we said that we define conformal dimensions of a field by its weights H and H bar, under which it transforms under scaling Z goes to lambda Z. So and if you look back at what Z was, so the fact that this particular Z goes to lambda Z was a linear combination of your, so if you remember this, so just going back 1-2 steps, as you see, L naught plus L naught bar is what gave you the dilatations, and IL naught minus L naught bar was what gave you the rotations. So that is, a direct consequence of that is that H is half delta plus S and H bar is half delta minus S. As you can understand, H plus H bar gives you delta and H minus H bar gives you S. Okay. Okay, we will get to this in more details as well. And we also said what the definition of a primary field is. This was given by equation 3.12. And if this equation 3.12 holds only for the global subalgebra, in that case, phi is called a quasi-primary field. So we ended up with the point that a primary field is always a quasi-primary, but not the other way around. Okay, so that was so then we looked at infinitesimal transformations and we got to the form 3.13, and then we said a few things about the energy momentum tensor, or the stress tensor, if you wish. So this as most of you know is defined as the variation of the metric of the action with respect to the metric. And if you look at the implications of conformal transformation out here, we discovered, of course, just by translation, we have the conservation of the stress tensor. And if we have a general transformation, then we saw that the trace of this was equal to 0. So we, at the end of the day, we saw that in a CFT, the energy momentum tensor is going to be traceless. I also just said that, yeah, even though I have mentioned this statement is actually going to be only classically true, and we will have some sort of deviations from this. We will see what exactly this is as we go ahead. All right, so now for a little bit of algebra. This is very simple, actually. If you are looking in 2 dimensions, then, as you know, T mu nu is going to transform in this way. And you can straightforwardly find that TZ, so your components will be TZZ, TZ bar Z bar, and TZ Z bar and Z bar Z. The fun thing is that TZ bar Z and Z bar, these 2 guys are related to T00 plus T11, which is the trace, and this has to be equal to 0, right? So these 2 guys are equal to 0. So what you'll end up with is you have two combinations, which is TZZ and TZ bar Z bar. These are the ones which are non-zero. Okay. Now remember, T mu nu, del mu, T mu nu equal to 0. So in that case, what you can do is you can rewrite this. So del 0 T00 plus del 1 T10 equal to 0. And the other way is del 0 T01 plus del 1 T11 equal to 0. So if you want to look at del Z bar of TZZ bar, TZZ, I'm sorry, or you have to resubstitute what del Z bar is. So this is del naught plus I del 1. And TZZ bar is T naught minus I T naught minus I T 10. And you just do the algebra, and you put in the fact that so you also just plug in that, for example, what do I want to do? Yeah, so you use the fact that here you use the fact that this is traceless. So T naught naught is going to be minus T naught 1. T11. That's a change from here and here. And these 2 guys, since T is T10 and T01 are the same, you can interchange these 2. And now what you find is that del Z bar of TZZ is equal to 0, right? So this is what you find. So what you have found, so similarly, you can also get that TZ of del Z of TZZ bar is equal to 0. So what you find is that the 2 things that we had that were non-vanishing, these 2 guys, one of them, del Z bar of this is equal to 0, and the del Z of this is equal to 0. So that means one of them is holomorphic, and the other is an anti-holomorphic function, or if you wish, a chiral and an anti-chiral field. So we will define TZZ. We'll devise a shorthand for this. We'll call this just T of Z, and we will call the other guy T bar of Z bar. Okay. So we will keep these in mind, and we will get back to these later in the class, or perhaps in the next class. Okay, that was a very elongated first recap of the last class, and some amount of new stuff with the stress energy tensor in 2 dimensions. So for the rest of the class, what I want to do today is actually look at some quantum mechanical aspects. So far, most of the stuff that we have done are classical. Some of them are not, but I want to clarify a few things in the class today. So we are, as I write here, we are going to turn to some aspects of the quantum theory that are especially important to, in a CFT. Okay. So firstly, what are local operators? Okay, so that's the first thing that I want to address in the class now. That's what local operators are. It seems that I have moved to the right. Just okay, so what I want to say first is local operators in a CFT are also called fields, and this terminology is a bit different from usual field theories. In a field theory, as you guys know, a field is some object that sits. You may not be familiar that much with path integrals, but no, that does not sit in the integral, that sits in the action. Actually, that is what I was trying to say here. So a field is some object that sits in the action and is also integrated over in path integrals. But in a CFT, what we are going to do is that a field is going to refer to any local expression. So these would include the usual QFT fields, but also include things like del n of phi. This is going to be a field, or you can also have some sort of composite object like e to the phi. So all of these are different fields in a CFT. Okay, so as you can understand, the set of fields in a CFT is infinite, even though in a field theory, in a QFT, usually one has a finite number of fields which are, which are also treated as fundamental objects. So this is just a change of language. It should not, that doesn't mean that things have got harder or something, but just remember this, okay? So I just wanted to point this out, that you may not be familiar, trying to call something like a del n x as del n of phi as a separate field, but this is what that one does out here. So what we are going to spend a lot of time in trying to understand in this class is what is called the operator product expansion, okay, or the OPE, okay. So the OPE is a statement of what happens when local operators are going to approach each other. When these approach each other, so the idea, in a sense, is that if you have two local operators which are inserted at nearby points, these can be closely approximated by a string of operators at one point. Okay, so let's denote all the local operators in a CFT by something called OI. Then what is going to happen is, some OI which is at ZZ bar and some OJ which is at omega bar, for example, they will be approximated by these functions Ci, Jk times a string of operators. You see there's a sum, a string of operators, okay, and now these guys are, at the point omega bar, okay. So theseCijks are going to be functions which, due to translational invariance, will only depend on z minus omega and z bar minus omega bar, but never quite there. Yeah, so it's going to be dependent on the differences, okay, since you have translational invariance built in. So for example, here you have something that is showing you, these two and these two particular operators, O1 and O2, these are close together, and there are several other insertions. We will get to what the circle is in a moment. Okay, So now it's an important thing that we need to, I mean, clarify here. Okay, so this particular equation 3.16, this only makes sense as an operator equation. So this is going to hold if these holds as when these operator insertions are inside, I mean, endpoint functions. So if you have a particular, I mean, endpoint correlation function that looks like this, and you bring these two guys close to each other, then you can replace this in that endpoint function by this, I mean, OPE. Okay, so for example, if you had, if you had what, say your operators are O1, say x1, O2, x2, O3, x3, and you have you are trying to take a limit of x1 goes to x2, then you can represent, you can sort of replace this by a sum over k of c I j k of, if you want, x1 minus x2, and you have a string of operators OK, and which is at the point x2, and then you have, okay, let me move this around a little bit so that I can give myself a little bit more space. And this particular thing becomes, sorry, horrible looking thing, O3 and x3, okay? So this is what the OP does for you. When you take these points x1 and x2 close to each other, then this guy is replaced by the string of operators at the point x2, okay? So the OPE makes sense when you are looking at when these things are valid inside some, I mean, endpoint function, okay? So whenever we speak of this, you need to keep this in mind, all right? Okay, now some more comments. So these correlation functions are always going to be assumed to be time ordered or something very similar that we will get to shortly. So this means that when you are speaking in terms of the OPE, everything is going to go through each other. So everything, I mean, operator ordering will not matter because the operators are already ordered inside this endpoint function. So it'll just mean that, this you can write as, I mean, OI, OJ, which is at Z and omega, or OJ, which is at omega, and OI, which is at Z. This particular operator, I mean, ordering, will not matter for the OP. There's obviously a, there, if you are dealing with, I mean, Grassmannian operators, obviously, if you want to pull them through each other, you'll get some signs. But I mean, if you leave that particular thing aside, this is something that you need to keep in mind, okay? All right, so another thing is that the other, I mean, operator insertions inside this, I mean, endpoint function, which were denoted by these dots out here, and which I gave you one example. These things are arbitrary, except for the fact that they should be at distances which are large compared to z minus omega. As long as those distances are large, that, I mean, the rest of the things will not matter. So in a CFT, rather remarkably, these OPs are exact, I mean, exact statements. OPs are exact statements, and these will have a radius of, I mean, radius of convergence, which is actually equal to the distance of the nearest other insertion. So this is something that we are going to return to later in the course. But this is what, I mean, the radius of, I mean, convergence is what is denoted by this, red circle out here, right? So this particular thing that you have out here is the radius of convergence of this OPE, and you see there is this point here which is just outside. I'm sorry. So this this point is just outside, and that is what that is what sets the radius, this particular radius of convergence, which is equal to the distance of the nearest next nearest insertion. As you can understand, these OPs will have a singular, singular behavior as z goes to omega. And interestingly enough, this is the only thing that we will, we would be interested in. Okay, we will for the rest of the terms which are not singular, we will just put some dots, and the singular terms will actually have the same information as this. Brackets and so on. Okay, so this particular thing about the OPE is something very important. So if there are any questions, I would want you to stop me right away and ask them.
Sir,
yes.
So we have assumed that product of two operators when they are close takes the linear form.
Mm-hmm.
It looks very nice and looks like an optimistic assumption, but is it an assumption, or is it something that you can deduce from something?
You will see. I mean, I would not be able to give you a proof of this, but this is so this is something. So you're saying what I mean, if there are composite operators or something weird goes on and so on and so forth. So we will see that this actually holds, and we will see that there is a way. So we have tried to, try to define things in one way, right? We have tried to look at what primary operators and things like that are, right? So we will rederive everything from this point of view as well. So I don't have a proof for you at the moment. I understand what you are saying. Let me try and give you a little bit more as we go further ahead, right? For a CFT, this is actually this particular thing becomes an exact. For CFTs, there is a proof for this as well. This is a proof that I am not absolutely familiar with. But let me see if I can actually find this out, okay? And if I can at least point you to a particular direction where this is actually worked out, or at least you have some more words to go on.
Sure.
Okay.
Thank you.
Yeah, sure.
Oh, also, these operators are the quantum fields, right? Or
these operators are quantum fields. In the sense that these are, so as I said, these are sort of all local operators, right? So it'll be the field phi, it'll be del of phi, del squared of phi, and so on and so forth.
Okay.
So the trick is, this sum is actually, this k runs over, all your operators. Okay. So the trick, that's what. So you're approximating something. You're going to approximate something, but there is a sum which is which is an infinite sum which sits here. Okay. So that's in a sense what what is going to allow you to do this.
Okay. Yeah. Okay. Thank you.
Yeah, sure. All right. So this is OPEs. And the next thing that we're going to be doing in the class today are called Ward identities. Okay. So Ward identities, what are they? So we have looked at, Noether's theorem in classical field theory. These relate symmetries to, conserve quantities, conserve currents, conserve charges. Now we want a quantum version of this, okay? And this is going to be an operator, operator equation that is going to capture the essence of Noether's theorem for quantum field theories. These guys, these operator equations will be called Ward identities, okay? So we will first start with a general discussion, then we will focus on CFTs afterwards. Given how I'm doing on time, I don't think I'll be able to get to the CFTs today, but let's sort of try and aim to get to an expression of Ward identities for a general field theory today. Okay, now, oops, sorry. Just a second, I lost my pen. Yeah, hi. So, seem to be missing something else. Anyway, yeah. So where was I? I was trying to write down what the path integral is, and so the path integral is of this form, and as we have said before, our phi is going to generate is going to represent all fields. Now, you know, by fields I mean fields in a field theory. I mean QFT sense, not in a CFT sense. So symmetry of the quantum mechanical theory is an infinitesimal transformation of phi prime goes to phi plus epsilon del phi that leaves invariant, as I said before, the action and the measure, both the action and the measure. So so what we are going to do, what we did earlier as well. So we are going to promote this, epsilon to, epsilon of x. So typically, neither the action nor the measure is invariant, but up to leading order, as before, the change is going to be proportional to del epsilon. Okay, so let's do this. So we have z, and z now goes to del phi primed exponential of e to the minus s of phi prime. Now we expand this out. So if you expand it out, so what is going to happen, as you know, I've put in these factors of minus root g in. Don't be too bothered about that. We can neglect that if you want. But we will have something which is an integral over, del epsilon multiplied by this j alpha, right? So this is very similar to what we have been doing in the classical case. Only the thing is that we have got some path integrals around right now. But so again, if you are going to keep things to just the leading order in alpha, leading order in the small parameter epsilon. So what you can do is you can take the exponent outside, and if you take the exponent outside, you're going to be left with two leading order. So you will have an exponential of this, and so that is going to give you to leading order. You're just going to get this. Now remember, the first line is, it is straightforward thing, right? So in this case, if the path integral has to stay the same, because of what? You know, if you looked at the first line, and if you looked at the way we defined the path integral in the first place, all we have done essentially is that we have changed the dummy variable of integration phi. So this expression that we have has to be equal to the the thing that we started off with. So that is the z. Okay. So in that case, this change, the change. So if this is equal to z, and then this particular change that we have, that has to go to 0, right? So this has to go to 0, and this is sort of the equivalent operator statement of this. Statement of this is that just this particular del alpha j alpha inside now this angular brackets which represent the fact that you have integrated it in this way. means that the this is an operator statement. Now, this last line holds since this integral equation here has to be true for all epsilon. Okay, so this, in a sense, is the quantum version of quantum version of Noether's theorem. All we have done is that we have invoked very similar things, but we are doing things in the path integral. So this turns out to be the correlation function, a statement of, this is an operator. This is an operator statement, if you wish. So that's what we can do for these. For this case. And now let's see if we can go ahead further and push this a little bit more. Okay. So instead of starting off with the partition function, you can now start off with something which is an endpoint function, right? So this endpoint function O1 to On is, as you know, given by the this particular partition function with these insertions of these O's. So let's look at this figure here. We are looking at figure A first. So what are we doing? We are going to put these insertions on a plane, and we are going to so these operators are sort of general expressions which are formed from the field phi, and under the symmetry of interest, these operators will change in a certain way. Let's say these operators change as OI, as OI plus epsilon del OI. Again, now to do the same thing, we're going to promote epsilon to epsilon of x. Okay, so I don't know why I have a sigma here. Let me erase this. So what we're going to do first is we're going to promote this. Sorry, epsilon to an epsilon of x. And at first, what we will do is that we will have a support for this only at a place where you don't have any sort of operator insertion. So in this particular region, epsilon is going to be non-zero. Outside it, epsilon is going to be all zero. Okay. Then this becomes trivial in the sense that it will just go through as before. So del I of OI just becomes equal to 0. What we had done before just goes through identically, and that just gives us that del alpha, J alpha of x, and all of these, x1 to x, O1 to On, which is at x1 to xn. This particular thing, the whole thing has to be equal to 0. And the point here to be noted is that x is not equal to xi. Okay. So when you have taken epsilon to have support, which is not in this, which is not coinciding with any of the insertion points, the statements, algebra and everything, the math will just go through in an identical way. And what you will find is that this particular thing is true. And since this holds away from all particular operator insertion, J alpha, del alpha, J alpha is equal to 0 is going to hold true as an operator equation. So this is very similar to what we had last time around. Okay. Now, what happens when you actually have an operator which is inserted at the same, at the same point? So, for example, now we are looking at figure B. Okay. Now we are looking at figure B, and now instead of the epsilon having support in a place where none of the O's are inserted, epsilon has support in a region here where you actually have O1. Okay, so the O1 is actually there, and this has support in this particular region. So what is the simplest thing that we can do? The simplest thing that we can do is we can take epsilon equal to I mean constant inside this shaded region and 0 outside. Okay, so let's do this. So if we were to look at the correlation function that we had from before, let's try to look at this. So we have this, right? So we are going to look at the change here. So the change here is going to be given when you are looking at the first piece. As you had before, this is going to transform into something like this guy. And there is going to be a change in the O1 as well. So O2 to ON stays the same. And so the change to leading order is going to be given by this integral, which is now going to enclose the place which is just epsilon, right? So what are we doing? We are going to change this. We are going to make the del alpha act on act on the rest of the things, and not epsilon. We need to put the epsilons outside. So what if you expand this out, then to leading order, what you're going to get is an integral that looks like this, and on the right hand side you're going to get the change of this guy, right? So what I mean is the following. So if you want, this is equal to 1 over z integral of del phi e to the minus s of phi into epsilon times delta O1 O2 dot On plus or minus, if you wish, as 1 over z integral del phi e to the minus s of phi. There's a 1 over 2 pi here. There's an integral j alpha del alpha epsilon. Goodness, I'm out of space. Okay, let me just try and clarify this a little bit more. Okay, so let's erase this. Okay, so let's take this guy and copy it, get another page, paste it. So what we want to do is we want to figure this one out, right? So this is what? This is 1 over z integral. So let's also try and understand this first step a little bit more. So you remember that what we were trying to do is the following. So we were trying to also look at this one, right? So this is sorry. So remember that the change that we had is going to be something like this. When we were looking at the change of z, then we saw that the change of z gives us something which is like this. So now instead of exponential of s, we have all of these operators also inserted, right? So when we have that, so we will get this term and the change. The change in the operator. So this is going to get multiplied by the thing that I just wrote. So this is the change. If you just had the partition function. This is just going to be that part of it. And so now here what we have is the change also for the O1 to ON. Okay. All right. So now what are we doing? So we are just writing this in the following way. We are just trying to write this as del phi e to the minus s 1 minus 1 over 2 pi integral j alpha del alpha epsilon. So this is O1 to ON plus epsilon del O1 O2 to ON. So this means what? This means 1 over z integral del phi e to the minus s O1 to ON minus minus 1 over 2 pi 1 over z integral del phi e to the minus s. What am I trying to do here? Yes, integral of j alpha del alpha epsilon O1 to ON. And then you have the other term, which is 1 over z integral del phi e to the minus s epsilon into del O1 to ON. So the change, if you wish, the change is going to be given by, so you want to isolate these two terms, and as we had said before, this has to be equal to 0, so the change has to be equal to 0. So this is essentially boils down to saying 1 over 2 pi 1 over z integral del phi e to the minus s integral del alpha epsilon O1, so O1 to ON. And what is this? This is just this guy, right? O1 to ON. This is equal to 0. Now, what do you do? Now you want to take this particular guy outside, and you want to do the integral, and you want to change this. Change the integral in the usual way. So what you end up with is you have to get you are doing the integral over this small small circle epsilon where epsilon is not non-zero, and you have pulled this alpha outside, and hence what you have is this correlation function that is equal to del of O1 and the rest of the guys. Let me just write down an ON for you somewhere here. All right, so that's basically what this is. So let me try and see if I can just clean this up a little bit more. Let's make this a little smaller. And pull this out a little. Put an ON here. Sorry for this. I just want to make sure that everybody is with me on this. Okay, so not a very happy thing to do. Okay, so that is what we wanted to do. So this particular integral that I have written out here is only over the region of non-zero epsilon. And this identity that I have written, this particular equation that I have written, this is called the Ward identity. Okay, so this is what your famous Ward identity is, and this is equivalent to the operator. So this particular identity is very important. Maybe a number of you have seen it before, but I thought it was important to re-emphasize this because we are going to be using this. And so what I want to say is this is going to be important to our subsequent analysis. In particular, we'll be interested in the question where the symmetry in question is conformal invariance in D equal to 2, and we will derive an expression for the conformal Ward identity in the next class. What I can do is I can just briefly give you, okay, so let's possibly postpone this discussion till the next class because there'll be a little more stuff. But what I wanted to just re-emphasize is that we have looked at two very important new sort of concepts this time around, and these two things were firstly, the idea of the operator product expansion. This is something that happens when local operators approach each other. So the idea essentially is that when these local operators are inserted at nearby points, and they can actually be approximated by a string of operators at one point, and that is what we tried to say here. And and we clarified several things, the first of which was the fact that this makes sense only when you are doing things inside an endpoint function. And and there were several more things that we tried to say out here, for that, since these are already inside these sort of endpoint functions, these are going to make sense. Why is there a K hanging around here? Anyway, I did something else. Yeah, so no, the K was there's a K here. For some reason, it got moved to that side. So we are going to be always speaking about, operators that are going to be, ordered in some way. You have come across time ordering so far. We will encounter something very similar as we go ahead. But so in that case, so everything inside the OP, actually commutes with each other, and the operator ordering is not important. And secondly, so we also said that the other operator insertions inside the correlation functions are not of importance, except for the fact that they should be at distances large compared to z minus omega. We will have something more to say about what the radius of convergence is, but for the moment, you can assume so we will see that it's going to be equal to the distance of the next nearest operator insertion. Okay, so that is something that holds true for CFTs. We have not proved this. I will try and give you some idea as we go ahead. And the most important things is that the OPs are going to have singular behavior as z goes to omega. This is going to be the only thing that we actually are interested in as we go forward. The non-singular terms will just denote with dots. The second important thing that we try to do today is we had a look at Ward identities. And Ward identities are sort of the quantum mechanical equivalent of what Noether's theorem is to classical field theories. So at first, we just showed you something to do with the path integral, and there we saw that we could write del alpha J alpha equal to 0 as an operator statement. But we could do more. Instead of just a path integral, we could try to play these tricks when we are looking at endpoint functions. And there we found that when this epsilon had support where there was no other operator insertions, that sort of boiled down to the same thing that we had before. But funny things happened when we took epsilon to have support inside a region where there was another operator O1. And in that case, what we found is that we had an identity that related this by this del alpha of J alpha inserted with the O's, with the change in the O's, if you wish. So this was the Ward identity at the end of the day that we derived, and that is going to be very important as we go ahead. Okay, so I understand that this class, for those of you who have seen this for the first time, may have been a little over the top. I will try and upload the notes as fast as I can, and also I'll try and give you some homework on things that we have done previously. So I hope you have fun with those. And if there are any questions and so on regarding this, or just try and read up a little bit more. Okay, so so try and make sure that you read this up before the next class, because we'll be going on to CFTs then, and we'll be using the Ward identities to rederive a few of the things that we have done. And this is going to be the idea of Ward identities, and OPEs would be very important as we go on ahead. Okay, so I am done speaking for the moment. So if you guys have any questions, please feel free to ask me, or if not, we can.
I have a question from the previous lecture, but
yes, please.
If there are other
yes.
questions, like maybe can I ask from the previous lecture, or
yeah, sure. Go ahead.
So there this like from the Witt algebra, like we centrally extended that to like to arrive at the Virosor algebra, right? So there it seems that in that process the number C can be complex. But if you're trying to identify with the central charge, shouldn't that be real?
We will get to all of that. Actually, we will get to all of that. It's not something that I have said. I have probably said the word central charge somewhere, but we will see all of that. So those will come from things like unitarity and so on and so forth. So that's some way away still.
Okay.
So all that we are saying is that you can extend it by something which is a complex number at the moment.
Right. Yeah.
So that is allowed by the closure of your algebra. That is allowed.
Yes. Right. Yeah. Okay.
So
thank you.
Yeah. Sure. Any more questions?
Sir, I also have a question.
Please.
About that central extension of the Witt algebra. When we extend that, is it the case that the new extended algebra, which is Virasoro, also is an algebra of some Lie group?
Yeah, see, what has happened is that when you are looking to exponentiate, right? So you need to make sure that your generators that you want to exponentiate, it has to be something that is well defined throughout the manifold, right? So now if you want to do that, the only part that you can actually look to exponentiate to get the group is only the part which is L0 and L plus minus 1. Now L0 and L plus minus 1 is obviously the global subgroup, and that does not have any central extension, as we said, right? So in that case, if you're looking for the group, it would not, I mean, it would not matter.
Okay, yeah, thank you.
But so interestingly, if you guys have read a little bit of Weinberg in your for your quantum field theory things last time around, maybe Niloy had gone through some amount of it. There's things called projective representations. Okay, so that actually deals with the with what you are. So central extensions are also related to that. So I will I'll try and give you guys an example of something that gives you a central extension for a finite algebra next time around. Yaman will probably be familiar with it, but well, I'll try and post that in the next few days. And if those of you who are interested should also look up Weinberg and look at the projective representations, because that's something of interest. Central extensions are I mean extremely interesting. Unfortunately, I don't really know much about the other way of trying to do it, which is essentially looking at this H2. So that's something it would have been good to give you guys. But if somebody, amongst you is proficient enough to, give me an explanation of, how to look for H2s, that would be great actually. So the floor is yours if you know how to do this. If you can come up with an analysis of these H2s of G, that would be nice. So yeah, so take that as as an exercise if there is somebody who is interested, so we can have side class or something like that if one of you would want to read up on that and just let us know what is happening with second second cohomology groups. Anyone wanting to volunteer for that? People are dropping off. Okay, but yeah, if you wish to, just drop me a line at some point of time. Okay. All right, so that's it for the day, and I will see you guys next week, and hopefully get you guys some homework in between as well. Any more questions immediately?
Sir, I just have a request. Can you upload the assignments on your website also?
Sure. I'll try and do that. It's just that I'm not. I'm not typing them up, so I'll just write them up. So, okay, I'll try and do that. Is it simpler for you to just do things from there?
No. I'm auditing the course, so I didn't receive any assignments.
Oh, sorry, Yaman. I keep forgetting.
It would work via mail also.
Yeah, sure. No. All right. I just. So I've been bad with these things. So there was only one so far, and these guys were asked to look at what the beta function of these this 5-4 theory was, and so that's what they did last time around. So I will do that, since there are quite a few of you who are just sitting in the course. If you guys want to actually solve a few of the things, so please, I will upload the assignments. It'll be handwritten as well, but yeah, hopefully my handwriting is something that you guys can read. All right, if there are no more questions, I will stop for the day, and I will see you all next time around. Okay, guys, bye-bye.